In this video, we're going to take a look at the binomial distribution, which is one special probability distribution. It's a discrete probability distribution, and it's just one that happens to show up a lot in real life, real world applications. So we talked in the previous video about the general idea of a probability distribution, and now we're going to apply this to some specific situations and see that there are some sort of special probability distributions that show up in certain scenarios. And this is the first one, the binomial distribution. So this just happens to be one of several that we're going to look at. This is just one of several useful probability distributions. And there's a whole bunch of other ones that we're not even going to look at. So we're going to look at this one, the binomial distribution. Later we're going to look at something called a normal distribution, something called a t-distribution, and there's a bunch of other ones. There's something called a Gaussian distribution and a chi-squared distribution, all these other things. And they all show up in very specific situations. We're not going to look at all of them. We're just going to look at a handful of the most common ones. Okay, so this is just one of a handful of several useful probability distributions. And it shows up basically whenever a simple probability experiment gets repeated multiple times. So what we want to do is keep an eye out for situations where a simple probability distribution, or sorry, simple probability experiment rather, with only two outcomes is repeated multiple times. Okay. So I want to give us sort of the conditions for a binomial distribution. Then I will give you some notation and a definition of the probability distribution. And until we actually do an example, which we'll do after all of that, a lot of this might seem kind of vague, but let's start by just laying out what it's going to look like and then going into an example. So here are the conditions. There are 5 conditions that have to be met for a binomial probability distribution to work. The first one is that we need a fixed number of trials. So the idea is a trial is just one repetition of this experiment. I said that we're going to repeat a probability experiment a number of times, multiple times. We need to know what that number is ahead of time. I can't just have it be open-ended and say, let's just repeat this experiment a bunch of times. I have to say, let's repeat it 7 times, or let's repeat it 10 times, or let's repeat it 100 times. We have to pick the number of times that we're repeating it. That's what I mean when I say we need a fixed number of trials. It has to be specified. The second condition is that there can only be 2 possible outcomes. And we have a little bit of leeway with this, as we'll see. So sometimes we can kind of tweak things that have multiple outcomes so that they only frame them in such a way that there's only 2 outcomes. But we want to have only 2 outcomes, and those outcomes should be success or failure. So we want to characterize every outcome as either a success or a failure. The third condition is that the probability of success needs to be the same for every single trial. So it can't change from one trial to the next. Every time we repeat the experiment, the probability of having a success has to be the same. The fourth one is kind of related to this. It says that the trials must be independent of one another. And in plain English, what does it mean for 2 trials to be independent? It simply means that the outcome of one does not affect the outcomes of the others. So the outcome of one doesn't affect the others. And the last condition is we need to define our random variable very carefully. We need to let x be the number of successes. Okay, so let me just run through a couple of examples of situations that may or may not meet these conditions, and we'll see that we've actually already encountered a lot of things that meet these conditions. And then I'll go on and actually give you the definition. So what types of scenarios are going to meet all of these conditions? One example that we could look at is something like our coin flip problem that we keep doing. So flip a coin 3 times. Does it meet all of these conditions? So do we have a fixed number of trials? Well, yes, because I specified that we're going to flip the coin 3 times. So condition 1, fixed number of trials. You can check that one off. Number 2, are there only 2 outcomes, success or failure? Well, when we flip a coin, we have 2 outcomes that are heads or tails. So we need to associate one of those outcomes with success and one with failure. So there are only 2 outcomes. We have heads and tails. We will characterize one of those outcomes as success and the other one as failure. Condition 3, is the probability of success the same for all trials? So skipping down, let me skip all the way down to 5, because this is where we define our random variable. So let's do this now. I'm going to let x be the number of successes, and in this case, I'm going to let that be the number of heads. So I'm going to let x equal the number of heads where we consider heads a success. So as long as I define it as heads is a success, then that means tails would be failure. And again, we only have 2 outcomes, heads, which is success, or tails, which is failure. So coming back up to the second point, we can see it now in that context. There's only 2 outcomes, heads, which is success, or failure, which is tails. Back to number 3, though. Is the probability of a success the same for all trials? Well, in this case, that's the same as saying the probability of getting a heads is always the same, which it is. It is always, on a fair coin, it is always 50%. The fact that I flip a coin and it lands on heads doesn't mean that I've used up a heads and I'm now less likely to get heads the next time around. Every time you flip a coin, it has a 50% chance of landing on heads. And that blends into point number 4 here, which is that our trials are indeed independent. Same idea. Does the outcome of one coin flip affect the other outcomes? No, and for the exact same reason. You don't use up heads if you land on heads when you do a coin flip. There's no using it up. So the trials are independent. And so flipping our coin 3 times meets all 5 criteria, and this will follow a binomial distribution. And that's really nice because I can change this from a 3 to, say, a 10 or 100. We can talk about the probabilities related to flipping a coin 100 times. Before, when we did this problem, we were relying on our tree diagram to come up with our sample space and figure out the associated probabilities. But now I'm going to have a formula, and I can make this number really large, number like 100, where we said a tree diagram wasn't going to be feasible for basically situations where we were flipping the coin much more than maybe 3 or 4 times. But now it doesn't matter. We're going to have a formula, and it'll work regardless of how many times we choose to flip the coin, as long as we decide ahead of time, let's do it 10 times or 100 times. Pick any number of coin flips you want to look at, and we can figure out probabilities associated with that probability experiment. It doesn't have to be 3 anymore. So this is going to allow us to solve a problem that we've already solved, flipping a coin 3 times, but it will also allow us to extend those same ideas to more complicated problems where we repeat the experiment a larger number of times. As another example, what if instead of flipping a coin 3 times, what if we are rolling a 6-sided die? And let's say we want to roll the 6-sided die 4 times. Well, in this case, we do have a fixed number of trials. Right? I've specified we're going to do it 4 times. So we're good on the first point. But then at the second point, we run into something that seems a little bit weird. We're supposed to only have 2 possible outcomes, success and failure. But the way that we've got this set up, rolling a die, there's 6 possible outcomes when you roll a die, not 2. So does that mean that this is broken? Not necessarily. It all depends on how we choose to define our random variable x. So let me label or put down all these numbers, and let's come back down to 5 and start with this. If I let x be the number of, say, 3s that we roll, or any other thing, then I can think of it as basically rolling a 3 equals a success, and anything that's not a 3 is a failure. So even though there's naturally 6 outcomes, I can group them in such a way that I consider anything that meets some condition I'm interested in, this case rolling a 3, that's a success, and anything that's not rolling a 3 is a failure. And now I've broken it from 6 outcomes, I've grouped them into just 2 separate groups of outcomes, successes and failures. And again, why did I pick 3? That was totally random choice. I could have picked let x be the number of evens that get rolled, let x be the number of 1s or 2s that get rolled, and anything that is a 1 or 2 would be a success, and anything that's not a 1 or 2 would be a failure, right? So as long as we find a way to group the outcomes, even though there's naturally 6, if we find a way to group them into the ones that we're interested in, and then everything else, then we can characterize those 2 groups as successes versus failures and treat it as though there are only 2 outcomes. So indeed, there are only 2 outcomes. If we frame this right, they are success and failure. So check. I'm calling rolling a 3 a success, rolling anything that's not a 3 is a failure. Is the probability of, in this case, our success, which is probability of rolling a 3, is that always the same for every trial? And the answer is yes. Every time I roll a die, I have a 1 in 6 chance of rolling a 3. So that number is going to be fixed. Every time you roll the die, you can't, again, just like you don't run out of or use up heads when you flip a coin and it lands on heads, you don't use up 3s when you roll a die and it lands on 3. The next time you roll the die, you'll have the exact same chance of landing on 3, which tells us that our trials are indeed independent. And these 2 points, point number 3 and 4, the probability being the same for all trials and the trials being independent, they are typically very closely related. Let me check off my number 5 and my number 4. I'll show us some examples down the line of how they are different. There are distinctions here, but they are very closely related. So we'll talk about that down the line. But basically, both of these scenarios are things that we've framed in such a way by our definition of the way that we've defined our random variable. We've managed to set them up so that they meet all of the conditions necessary to follow a binomial distribution. So what is a binomial distribution? Well, for one thing, it's called the binomial distribution because it involves only 2 outcomes, success and failure, right? So the bi part of binomial is an indication that we're talking about a situation where there's only two possible outcomes. So what is the binomial distribution? Let me give you a little bit of notation, and then let me give you the full definition. So here's some notation that we'll need. There are going to be a few different symbols that show up in this formula. The first one is going to be n, lowercase n, and it's going to be the number of trials. So if you think of this as us repeating this experiment over and over, n is sort of our sample size of the number of experiments. In this case, the number of trials. We are going to have a lowercase p. Lowercase p is going to be the probability of success for one single trial. Right, so up here when we talked about the probability of 3, where 3 is what we're considering our success, the fact that that's the same for every trial, in this case, it's 1 in 6, right? You have a 1 in 6 chance of rolling a 3. That would be our p for this problem. Up here we said probability of heads. We're considering heads to be a success. The probability of landing on heads is always the same for each trial. It's always a half. So for this example, the lowercase p that we're using would be a 0.5 or a 1/2. And down here, it would be 1/6. That's the value. We're also going to have x, which is going to be basically the outcome of interest. So the value of the random variable that we're interested in computing the probability of. So of interest. Okay. So with this notation and with those 5 conditions satisfied, we have the following definition. So if the 5 conditions above are met, then we have the following definition. A binomial random variable x binomial random variable, which again we're going to use capital X for, representing the number of successes, each with a probability p. So in n total trials, gives the probability of obtaining that lowercase x number of successes. Okay. And that formula, let me put it a period there, looks like the following. So let me write this down and then we'll come back to it and talk about what it means. So it's going to be ncx p to the x 1 minus p to the n minus x. Okay, so here's a big scary formula and a big scary definition. And so let's come back and revisit this thing now that we've got it written down. Okay, so our binomial random variable x, which represents the number of successes out of n trials, is going to give us the probability of obtaining x successes. So if I'm interested in obtaining lowercase x successes, that's the value of the random variable of interest, this is the formula that will give that to me. And it's broken into sort of 3 parts. This first part is the weirdest looking part. These 2 letters, the n and the x, are meant to be subscripts. So they're kind of tiny letters that are down from this big capital C. This thing is called the combination function. And I want to give you a little bit of a sense of what it does in just a minute, but let me talk about the other parts first. So this is the first part. And then the second part is this p to the x. We have the probability p raised to the power of x. If you happen to look into, if you did the optional section 5.3, if you looked at that, it gave us a multiplication rule. And it said basically when you repeat something over and over and they are independent trials, you wind up multiplying the probabilities. And in this case, we have independent trials, and we're repeating this thing x number of times, or hoping for x number of successes. That would mean that the probability of success had been repeated x times. So it would be p times p times p times p, x total times. And so we write that as p to the power x. Exponents like this just imply repeated multiplication. And then over here, 1 minus p, if p is the probability of success, then 1 minus p is the probability of failure. And if we had x successes out of n total trials, then whatever's left over must be the number of failures that we had. So if we had x successes, and then we have n minus x total number of failures. So this is the same thing. This has to do with the number of failures that we have, raised to the power of how many failures there were. So the probability of failure to the power of how many failures we expected, probability of success raised to the power of the number of successes, and then this combination function. All of this is to say that basically when we apply this formula, we are going to be using technology. This is not a nice formula to do by hand, but let's take a look at it and use it in the context of an actual example and see how this works. So let's focus first on this combination function so that you can have a sense of what this means. And again, the combination function is not something down the line that I'm expecting you to do any of this by hand. All of this stuff is going to be done on the calculator or in Excel. But I want you to at least have a sense of what's going on. What does this combination function mean? You may have, if you've taken other classes, you may have heard of this function referred to as like n choose x. If not, that's totally fine. But what does it do? This gives us the number of combinations of size x out of n total objects. The combination function is going to tell us the number of combinations that you can come up with of size x out of n total objects. So for example, let's do an example of this. We have 3 marbles. So hypothetically, we've got 3 marbles, 3 objects. Red, yellow, and blue. So one is red, one is yellow, one is blue. I want to look at the combination function for this thing. So in this case, because we've got 3 marbles, it tells us that we have 3 total objects. So our n is 3. We have 3 total objects, 3 marbles in this case. I want to figure out how many combinations we can make of the various different sizes x. So I want to let x be equal to 0. I want x to be equal to 1, x equal to 2, and x equal to 3. These are the different cases I want to look at. We'll come back to this x equals 0 case last because it's kind of the least intuitive, but it makes more sense once we've got the other ones. But let's look at x equals 1. What I'm basically saying is, looking at this formula, the combination function, I would write this as 3 with a big C and then the number 1. What this means is I have 3 objects and I want to choose one of the objects. And I want to know how many different ways can that be done. So we're going to use set notation, just like we did back when we were talking about probability, but with these 3 objects. So if I have a set, let's put my set notation around these objects. Here's the 3 objects I have. I have a red marble, a yellow marble, and a blue marble. How many different ways are there to pick one marble out? Well, I could pick out just the red marble. There's one way I could pick out one marble. Or I could pick out just the yellow marble. Or I could pick out just the blue marble. How many different ways were there? That's 3 total ways. We have 3 different ways that we can pick out one object out of 3 total objects. So 3C1, 3 combination 1, or 3 choose 1, this winds up being equal to 3. There are 3 different ways that we can get 3 different combinations of one object out of 3 total objects. How many different ways are there to pick 2 of the marbles? So if I have 3 marbles and I want to choose 2 of them out, how many ways could I do that? Well, one I could pick out would be the first 2. I could pick out the red and the yellow. So that's one combination of 2 of the 3 objects. What's another combination I could pick out? I could pick out the red and the blue. That's a different combination of 2 marbles that I could pull out. Or I could pull out the yellow and the blue. And after this, you might say, well, I could also pick out the blue and then the red. But that's not how we're going to treat this. This is not going to work this way. What am I highlighting here? Blue and the red marble is the same as the red and the blue marble. These 2 are the same thing. The idea is I don't care which order I pulled the marbles out. If I've got the red and the blue in my hand, I could call that red blue, I could call that blue red. It doesn't matter. They're the same thing. So this isn't a different outcome. Any other outcome that we can come up with, so like yellow red, well, that's the same as red yellow. Blue yellow, well, that's the same as yellow blue. So even though we can come up with different combinations where we switch the order, we don't care about the order. The idea is I just want to see which 2 marbles I have left in my hand. I want to pick out 2 marbles and I want to look at them. And I don't care the order. There's no order between them. Blue red is the same as red blue. And so with that in mind, I'm going to ignore this one, ignore any repetitions, and it turns out, again, I've only got 3 different combinations in this case. So there's 3 of these as well. So when I do 3C2, that is also 3. So basically, this part of the function is just going to be spitting out a number. And I'm showing you here what the numbers are that it's spitting out. Let's go down to this one. How many ways out of 3 objects can I pull all 3 objects out? Well, again, because we don't care about order, there's only one way to pull all 3 objects out. You just pull all 3 marbles out. If you pull all 3 marbles out, there's only one way to do that. So in this case, there's only one. This tells me that 3 choose, let's write that in the right order. Let me just delete this for now so I have more room. This tells me that 3 choose 3. How many ways are there to choose all 3 objects? There's only one. I just take all the marbles out. There's only one way to do that. How many ways are there to take out 0 of the marbles? Well, same thing. If I take out none of the marbles, I would just do the brackets with nothing in them. That's called the empty set. There's only one way to do that. There's only one way to pull out none of the marbles. Don't pull out any of the marbles. That's the only way to do it. So this is also 1. So in this case, 3 choose 0 is equal to 1. And so we found that basically there's only one way to pull out none of the marbles. There's 3 different ways to pull out just 1 marble. There's 3 different ways to pull out 2 marbles. And then there's only one way to pull out all the marbles. And we can extend this to more objects, but it gets a lot more complicated. We're not going to be able to just do it off the top of our head. So there's a formula that will generate the numbers that we're getting here, the 1, 3, 3, and the 1. It comes from something called Pascal's triangle, if you've ever heard of that. Comes from something called a binomial formula, and that binomial formula involves exponential functions, which sorry, not exponential, factorial functions, which involve a symbol that looks like an exclamation point and means basically, so like the number 3 factorial is equal to 3 times 2 times 1. You multiply that number times every other whole number smaller than it. 4 factorial would be 4 times 3 times 2 times 1, and so on. So there's a big ugly formula. But again, I don't want to scare us with big ugly formulas and worry about that math. We're going to be doing these using technology. But there are just a couple of cases that are kind of good to have off the top of our head. And one of them is, no matter what the number of objects is, if I do n choose 0, so n could be 100 objects. I have 100 marbles, or I have 10 marbles, whatever we want. How many ways are there to choose none of them? Well, it's always going to look like this. There's always just one way to pick nothing out of that set. Right? It's just the empty set. There's always one. So no matter what the first number is, if the second number is 0, n choose 0, you're always going to get 1. Similarly, if we do n choose n, how many ways are there to pick out n objects out of n objects? So choose all of the objects. How many ways are there to choose all of them? Same thing that we saw here. You just take all of them out. Right? This would also be only one way, right? If I extended it to red, yellow, blue, green, orange, violet, whatever. If this was my big set, and I now have 6 objects, what is 6 choose 6? What is the one way to take all 6 objects out? You take all 6 objects out. There's only one way to do that, right? Because we don't care about the order. So you just take them all out. This is only one way to do it. So n choose 0 is always going to be 1, and n choose itself, if the number is the same on both sides, that will always be 1. How many ways are there to do n choose 1? So same idea as what we did here. If I've got n objects, so instead of 3, let's say I've got 10 marbles. This number was 10. How many ways are there to choose 1 marble? Well, I could choose just the first marble, or just the second marble, or just the third marble, or just the fourth, or just the 5th, 6th, 7th, 8th, 9th, or 10th. If you're just picking one out, you're going to get n. There's n ways to do it. And we saw that pattern here, right? When it was 3 choose 1, when we had 3 marbles, there's 3 different ways to pick out 1 marble, because you're just taking out just that first marble, just the second, or just the third. Same thing if this was 10 marbles. You could pick out just the first, just the second, just the third, just the fourth, dot, 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 all the way up to just the 10th. So no matter what n is, n choose 1 will always be n. And this one is probably the trickiest. What is n choose n minus 1? So what I'm saying is, how many ways are there to pick out 1 less than the total number of marbles? So if n was equal to 10 here, I'd be interested in 10 choose 9. How many ways are there to pick 9 of the 10 marbles out? And that question is kind of scary and difficult. How many ways are there to pick 9 of the 10? Right? That means coming up with crazy combinations like this, but now there's 9 objects in each of these out of 10 total objects. So it's scary if you think about it that way, but it's easy if we think about it a different way. If I've got 10 objects, and I want to figure out every way that I can pick out 9 objects of those 10. Another way to think about picking 9 out is, how many are we leaving behind if we pick 9 of the 10 out? That means we're leaving 1 marble behind. So how many ways are there to leave only 1 marble behind? Well, I can leave just the first marble behind, or just the second, or just the third, or just the fourth, or just the 5th, or dot, 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 all the way up to just the 10th. So this is also going to be n. There are n ways to leave 1 marble behind, right? So instead of thinking about it as picking 1 marble out, there's n ways to pick 1 marble out. There's also n ways to leave 1 marble behind. And so these are some sort of special cases that are kind of nice to know off the top of your head. We won't necessarily need this information on exams and stuff, but it can help kind of streamline the process for some of these if we're if we luck into one of these cases, then maybe we can do it without the calculator. So for example, let's figure out if we can use, so let's put the whole binomial distribution formula to use. Let's do some more examples. But I want to come back and now that we kind of understand this part of the formula, I want to use the whole formula for some examples. So let's just do the coin flip example. Let's just verify that this is going to give us the same results that we were getting before. So I want to flip a coin 3 times. And I'm going to let x be equal to the number of heads that we get. So we've already done this problem. We looked at this and we figured out the probability of getting 0 heads, 1 heads, 2 heads, or 3 heads. Those are all the possible values of x that we can have. But we can figure out these probabilities now using our formula because we've already seen flipping a coin 3 times right here, it satisfied all 5 of the conditions. So this satisfies a binomial distribution. That would be our first step, is evaluate the situation and verify that the scenario we're talking about, flipping a coin 3 times, verify that it meets these 5 conditions. So do we have a fixed number of trials? Yes, we're flipping the coin 3 times. Are there only 2 outcomes, success and failure? Yes, heads is success, tails is failure. Is the probability of success always the same? Yes, we always have a 50% chance of landing on heads, so it's always going to be 1/2. Are the trials independent? Yes. Flipping the coin, whatever I got on my last coin flip has no bearing on what I'm getting on my next coin flip. And lastly, did we let x, our random variable, be equal to the number of successes? And the answer is yes. As long as we're considering heads to be successes, x is the number of successes. So we've got all 5 of our conditions. So that means if I want to know what is, zoom back in here, what is the probability of getting 2 heads? Out of those 3 coin flips. So in that case, we're saying x, the number of interest, is 2. I'm interested in getting 2 heads. N, the total number of trials, is 3. And p, the probability of a success for 1 trial, is 1/2. Or we could write that as a decimal, 0.5, right? The probability of landing on heads for 1 trial. And I can put these into my formula. The binomial formula says the probability of x is equal to ncx, p to the x, 1 minus p to the n minus x. And so when we plug in these values here, what we're finding is the probability of getting 2 heads, right? Because x, this x here, is the same as this x here. It's the number of successes that we're interested in this particular case. And I'm going to get 3 choose 2, or 3 combinations of 2. P was 0.5. We're raising it to the power 2 because x is 2. 1 minus 0.5 raised to the power 3 minus 2. So all I've done is everywhere an n shows up, which is here and here, I've plugged in 3. Right? So we have a 3 here, a 3 here, in these 2 places. Everywhere x shows up in the formula, I've plugged in a 2. So here, 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 and here. Here, 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 and here. And everywhere a p shows up in the formula in these 2 locations, I've plugged in this value p, which is 0.5. So here and here. We just did 3 choose 2 a minute ago. 3 choose 2, how many ways were there to select 2 marbles out of the 3? That was 3. So that part of the formula becomes a 3. Over here, if we want to write this as a fraction instead, I guess I could have written it, and maybe that'll be easier to recognize because we did it with fractions before. So let me change these 0.5s to fractions of 1/2. That'll make life a little easier. So here I've got 1/2 squared. We'll come back to that in a minute. And then what do I have over here if we simplify things? Well, I have 1 minus 1/2 inside the parentheses. What is 1 minus 1/2? That is also 1/2. If you take away 1/2, you're left with the other 1/2. And what power is it being raised to? 3 minus 2 is to the power 1. And so if we carry out these multiplications, I've got 3. The power 1/2 squared, I square both the top and the bottom, so multiply it by itself, 1/2 times 1/2. 1 times 1 on top will leave me with 1. 2 times 2 on the bottom will give me 1/4. And then 1/2 to the first power, anything to the first power is itself. And so here is the product that I've got. And in the numerator, if we want to think about that 3, if you get scared by multiplying fractions, you can always rewrite any time you see a whole number. You could just write it as that number over 1. So I'm rewriting that 3 as 3 divided by 1, which is still 3. And now when we multiply fractions, it's easy. You just multiply across the top, multiply across the bottom. So on the top, I've got 3 times 1 times 1. That's still going to be 3. Multiplying by 1 doesn't do anything. And on the bottom, I have 1 times 4, which is still going to be 4, times 2, which is 8. And we get the answer 3/8. What was the answer when we did it before, using our sort of tree diagram to come up with the sample space and then counting through the values in the sample space? We got the exact same thing. We got 3/8. So we can use this formula to generate the values that we got when we did 3 coins, but we could just as easily now use this formula if we were flipping the coin 10 times or 100 times. And it was just a matter of plugging into this formula. The tree diagram wasn't going to work. It was going to be too complicated, but this formula works totally fine. Okay, so down the line, we'll look at some more complicated examples, and we'll do some of these problems on a calculator and in Excel. But let me talk about a few more scenarios, and then I want to go over some statistics related to binomial random variables. So, when can we use this approach? Well, we already saw those 5 conditions have to be met. And so we said this coin flip example, we were able to make it work. Even the dice roll example, we were able to make it work. But what about some other scenarios? What if we are dealing cards from a deck? So let's say in this example where we're dealing cards from a deck, let's say let's deal 10 cards from a nice randomly shuffled deck, and let X be equal to the number of kings that we get out of that deck. Okay, will this meet those 5 criteria? So number 1, do we have a fixed number of trials? Yes, so let me just do a check mark. Yes, we're dealing 10 cards. We're randomly picking a card from a deck 10 times. So we're repeating this process 10 times. We have a fixed number of trials. Number 2, are there only 2 outcomes, success and failure? Well, the answer is, again, yes. As long as we let X be the number of kings and say that drawing a king is considered success, then drawing a king is a success, drawing any other card that's not a king is a failure, and we've characterized it as success versus failures. So all that requires is for us to, again, go ahead and skip down to number 5. As long as we let X be the number of kings, which is what we defined, and let that number of kings be the number of successes, then check. We've broken it down, and we've satisfied this 5th criteria as well. So criteria 3, is the probability of a success always the same? And similarly, are the trials independent? Because we've seen that these 2 ideas are often related. Well, in this case, the way that we typically deal cards is we pull them from a deck and we pull all 10 cards out. We don't pull 1 card out, check and see what it is, and then shuffle it back into the deck. So with this in mind, when I pull the first card out, what is the probability of a success? So if there's 52 cards in the deck, and 4 of them are kings, I have a 4 in 52 chance of success that first time I pulled a card out. And if on that first time I pull a card out and it's not a king, what's my probability of success the second time around? Well, I went from 4 out of the 52 being kings to that was after the first trial. After the second trial, or during the second trial, we've assumed that we didn't get a king the first time. That means there's still 4 kings in there, but how many cards left? 51. And so the probability has changed. Or maybe we went from 4 out of 52 the first time, and the first card we pulled was a king. And in that case, how many kings are left the second time? Well, we're down to only 3 kings. But again, there's also only 51 cards left. In both cases, the probability of success is changing from one trial to the next. So if this is the trial. And that means that the outcome of one affects the probability of the next, right? Pulling something that wasn't a king the first time led to this result, this probability for our second trial, whereas pulling a king the first time led to this result, this probability for our second trial, and they're different. The outcome of one affects the probability of the next one. So in these cases, both of these are not satisfied. So without replacement, meaning without replacing the card back into the deck, this is not a binomial distribution. However, if we did, when we draw these 10 cards, if we just drew them in order, but then shuffled, so draw one card and then shuffled it back into the deck before we draw our second cards, then this would work. If we were replacing the cards back into the deck each time we look at one, this would work because every single time after we checked whether or not we'd got a king, we'd shuffle that card back into the deck and we'd always be dealing with a 4 in 52 chance of pulling out a king. So this is an important concept, replacement versus lack of replacement. If you replace a card back into the deck, it is a binomial distribution. If you don't replace the card back into the deck, which is the way that we normally would play cards, then it's not a binomial distribution. So replacement is very important here. It determines whether or not this is going to work. And again, by replacement, all I mean is after each trial, are we putting whatever was just drawn, does it go back into the pool of possible things that could be drawn again? Okay, so with this in mind, let's look at a couple of other examples. So we just did dealing cards from a deck. Here is the one that we actually care about. This is the one that I wanted to lead to. So we've done flipping coins, rolling die, dealing cards. Everything so far has been gambling themed. Can we find an example that's not gambling themed? And here's the idea. I want to take a simple random sample of maybe 100 voters. Let's let X be the number supporting some specific candidate, candidate A, as opposed to candidate B. Will this follow a binomial distribution? Because it'd be awesome if we could apply that simple formula, even though it looks scary. It's going to be simple when we do it on the calculator in Excel. It'd be awesome if we could apply a formula to figure out probabilities related to this. So here's my 5 criteria. Do we have a fixed number of trials? Yes. We are doing basically a simple random sample 100 times. We're picking 100 people out of the crowd. this presumably maybe it represents, maybe we're talking about a mayoral election. This is everybody, we're picking 100 voters in Albuquerque. Maybe it's the presidential election. We're picking 100 voters across the entire country. But basically, we are randomly picking a person out of the big population, whatever that population is, 100 times. We're repeating this trial 100 times. So we've got 100 trials. Number 2, are there only 2 outcomes? And again, the answer is yes. They either support candidate A or they don't. So support A equals success. It doesn't even have to be that only 2 candidates are running, right? It's not you have to support candidate A or B. There could be A, B, C, D, and so on. But the question isn't which candidate do you support. The question is a yes or no question. Do you support candidate A? Yes or no? So if you support A, that's a success. If you support anybody that's not A, that's a failure. So yes, we can frame this as having only 2 outcomes. So as long as X equals number supporting A, which is the definition that we used right here, as long as that's the definition that we use, we've let X be the number of successes. And here come the 2 tricky ones. So we've got all of these set. Is the probability of success always the same? And are the trials independent? And the answer to both of these is no. We are not going to have the exact same probability of success because it's the exact same issue we ran into right here. Typically, the way that one of these polls is done, once you poll somebody and you ask them, the survey that you're asking them, you don't put that person back into the pool of possible people that could be picked again. So both of these, the answer is no. Right? If I pick out, in the first time I run my trial, if I pick out somebody that does happen to support candidate A, then when I go to interview the next person, pick my second person, there's one fewer person that supports candidate A in that pool of likely voters that I'm going to be addressing. I've changed it from maybe it was 500,000 out of a million, and now it's 499,999 out of 999,999. The probability didn't change much, but it did change a little bit. So the answer is technically no to both of these. Technically. But, and this is a really big but, we can still make it work. And so this is a really, really important point, right? The idea is the binomial distribution has a formula that we can use to figure out probabilities. It would be awesome if we could use it. Even though we technically can't, can we get around that? And so here's the argument for why we can get around that. If the sample that we're taking is less than 5% of the total population, then the effects of replacement versus no replacement, non-replacement, I guess I should say, are negligible. And we'll just ignore it. So think about what this is saying. It's saying if our sample is tiny compared to the overall population, then we don't really care whether or not we're using replacement versus non-replacement. Why not? Because if you have a really big population and your sample's tiny, what are the odds that you would have picked somebody twice in your sample anyways? So imagine that you did take everybody you sampled and then you put them back into the population after you'd sampled them, and it was possible that you could wind up sampling that same individual again. If you're only sampling 100 people, and the city that you're in is 1 million people, what are the odds that any of those 100 people would have gotten picked twice anyways? It's possible, but it's very small. It's so small as to make it so unlikely that it really doesn't make a difference. And so that's kind of the idea behind this. If your sample's tiny compared to the population, if you're pulling from a very large pool compared to how big of a sample you're going to take, the odds of picking somebody twice are basically, they're slim to none. So it doesn't matter if we're not replacing people, because even if we were, we probably wouldn't have picked them twice anyways. And so it really isn't going to make a difference in the results. So technically, the formula that we get will give us a result, and it'll be off, but it'll be off in like the 6th decimal place or something. We won't care. The difference will be negligible. So even though these people that are sampled, it's still, the results are technically not independent. They're so close that we're not going to care. And so this is our cutoff. Again, as long as the sample is less than 5% of the population, the odds of picking someone twice even with replacement, so even allowing for that possibility, are slim. And so it's not going to actually affect the end result. So we will treat this simple random sample scenario as a binomial distribution, as long as our sample is tiny compared to the population. This is a really important thing. We are going to be utilizing this all the time because these are the types of questions, again, that people are actually interested in. This is where probability and statistics actually becomes useful, is to answer these types of questions. It's not just card games and dice games and coin flips, right? It's not all just gambling. If we have questions related to medicine and biology and economics and politics, these are the types of questions that we're going to be interested in. These are the types of surveys that we'll be conducting. And it would be really nice if we had some rigorous mathematics, a rigorous formula that we could use to get some idea about probabilities related to scenarios like this. And as long as we make this assumption, we're going to be able to use that binomial distribution formula. Okay. I will give you another example of actually using the binomial distribution when we do this on the calculator and or Excel. But for now, I'm going to skip doing another example of applying that formula. And instead, I want to talk about some statistics related to the binomial distribution. So in the last video, we had statistics for a general probability distribution. We talked about the mean, the variance, and the standard deviation. I gave you some formulas, and then we did the example with the game of roulette. So looking at roulette, we used those statistics to figure out the expected value, how much money we would expect to win, or in that case, lose, placing a $1 bet on the game of roulette. We have very similar statistics for binomial distribution, but they're simpler. And so I'm going to write out the statistics for a binomial distribution. So these are for the binomial distribution only. When we're dealing with a binomial distribution, this particular type of probability distribution, we don't need to use those general formulas from the last video. We're going to have easier ones. So it turns out, if we want to compute the mean, the expected value, it's simply n times p. If we want the variance, so sigma x squared, it is simply np times 1 minus p. And lastly, if we want the standard deviation, which is just sigma x, it is the square root of np times 1 minus p. Okay, so let's think about what this means and how this works. So this was as opposed to, just to make it totally clear, as opposed to the formula that used to be this, sum of x times p of x. Right? This was the formula that we had in the previous section. This is the general one for general probability distributions. But if we're dealing with a binomial distribution, I can use this one, and it's much easier. There's no sum involved. It's just a single multiplication between n and p. Remember what n and p are. So let's say, again, let's say we want to flip a coin 10 times. Find the expected number of heads. Okay. So the expected number is the expected value. Again, we can use this symbol if we'd like, e of x, or we can use the symbol that we used up here, which is mu sub x. Right, so this symbol right here, remember that can also be written e of x for expected value. But it's simply n times p. Before we even plug into this formula, you can probably answer this question. If I flip a coin 10 times, how many times would I expect it to land on heads, on average? So it may not happen the first time, but if we repeat the experiment a bunch of times, so I flip a coin 10 times, record how many times it lands on heads. Do it again, flip a coin 10 times, record how many times it lands on heads. Do it again, flip a coin 10 times, record how many times it lands on heads. And I take the average of all of these results. How many times do you expect that coin to land on heads out of the 10 times? Well, I expect it to land on heads 5 out of those 10 times because I expect it to land on heads half the time. And that's exactly what this tells me. N is the number of trials, and P is the probability of, in this case, success of heads. And so all I need to do is take 10, the number of trials, and multiply it by the probability of success, half. I expect it to land on heads half the time. What's half of 10? 5. That's all the formula is doing. The formula is exactly what your intuition is probably telling you anyways. So that is the idea. Same thing, you can apply this same idea and plug into these other ones. So if I wanted to know what the standard deviation was in the number of heads, so find the, if we wanted to find standard deviation in the number of heads. So basically, on average, right, it's not always going to land on heads 5 times. Sometimes it'll be 3 times. Sometimes it'll be 4 times, 5, 6, 7. Right? It's even possible that it doesn't land on heads at all, or that it lands on heads every time, but those are unlikely. And it's just asking, on average, how far will we be from the 5? How consistently are we going to get close to 5? That's what the standard deviation is telling us. And we can figure that out by just plugging in. So I'll plug into the formula. N times P is again 10 times a half times P, which is 1 minus P, which is 1 minus 1 half. And so I've got the square root of 10 times a half. The 1 minus half was also a half. If I multiply these all together, what's a half of a half? Half times a half is a fourth. Fourth of 10 is 2.5. So this is the square root of 2.5. What do I get when I get the square root of 2.5? Let me do that on the calculator real quickly. So second square root, 2.5. I get 1.58-ish. So there's my answer, 1.5. On average, it's going to land on average, it's going to land on heads 5 times. But for any individual trial, on average, I'd expect it to be either about 1.5 above or below 5. So, on average, if you take into account the times that it lands on 5, 4, 3, 2, 1, and 0, and average those all out, you'd wind up with it landing on a number about 1.5 away from the 5 that you were expecting. So sometimes it'll be below, sometimes it'll be above, and on average, you'll wind up getting 5. But it's on average 1.5 away from that 5. So it's telling us basically how spread out are the results. Okay, so watch the other video where we're going to do problems like this using technology, the other videos, I should say. And we'll do another example there. And that is the way that I would expect you to do these problems on homework and exams and so on. So make sure that you get comfortable doing this using technology, because that is going to be the more useful skill.